Hello, in this presentation I will be talking about polar codes, operation and performance over wireless channels. The outline of this presentation is as follows. First, I will start with an introduction, then how to construct polar codes, then how is the channel combining and channel splitting is done over a channel, and then some advantages of polar codes. Then my friend will talk about polar codes performance over wireless channels for image transmission as well as speech transmission. Then we'll finalize our work with a little conclusion. First, the polar codes were proposed by Ari Khan. They are the first capacity achieving family of codes with a low encoding and decoding complexity. Channel polarization actually is the key technique for achieving polar codes, and mainly the application of polar codes is its usage over multiple over wiretap channels, quantum channels, and multiple access channels. Throughout the rest of the presentation, we'll discuss the operation of polar codes and its construction and its performance over wireless communication channel. Polar coding is a coding method that aims for achieving symmetric capacity described by the mutual information IW. Symmetric capacity is the maximum capacity that can be theoretically can be achieved over a channel, and mainly it's achieved whenever the probability of the input is equal. In this method, the method of polar coding, a discrete memoryless channel is used for n independent times with the purpose of producing n channel. And in these channels, the fraction of indices for which IWIN goes to 1 approaches IW, and also the fraction of indices for each IWI of n goes to 0, approaches 1 minus IW. This property actually is called channel polarization, where the mutual information is either polarized at 0 or at 1. Thus, code generated by polar coding is a block code of length and with encoder and decoder complexity of order n log n. And since the n uses of DMC channel are independent, the transition probability can be given by this formula. And actually, the transition probability can be given by the transition probability of the other n channels since they are independent. In the process of polar codes, the channels are polarized in a sense that half of the n channels will have capacity closer to IW, while the other half will have the capacity closer to 1 minus IW. Thus, the channel's capacity with capacity close to IW will be used for coding, and the rest will be fixed. The process of channel polarization will be divided in two steps: channel combining and channel splitting. First, I will start by talking about channel combining. In this phase, n independent DMCs are combined into WM channels that the input xn and that has an input xn and an output yn. In the slides, we will take an example of how to construct a W2 channel, which is like two DMCs where two NDMCs are combined. The input of the first channel X1 is XORed with the XOR of the two inputs U1 and U2, whereas the input of the second channel W is just U2. And this method can be generalized to how to take it for a WN channel, where like it is subdivided into two WN over two channels, and where the input will be passed through a permutation operator, which is a shuffle matrix. So assuming the input of the XOR process is S is then will be fed to the permutation operator, which in turn produces an output Vn, and Vn will finally be used as an input for the two Wn over 2 channel. Now for channel splitting, as we said in the previous step, which is channel combining, n uses of DMC help us to build a synthesized WN channel. Now this channel needs to be split again into n polarized channel. Out of this n channel, we will only use those with capacity close to IW. The transition probability for the n channel will be defined in this equation, where y1 and u1 I minus 1 is the output of the ith channel and ui is its input. Mainly the advantage of polar coding can be summarized as follow. First, polar coding achieves a capacity very close to IW with a low complexity for both the encoder and the decoder. And also the encoder and decoder of polar codes have a complexity of order n log n. Mainly we compare the polar codes to LDPC codes, and it shows that the decoding complexity of the decoder is the same, but in both of the cases, like LDPC and polar codes, but that of the encoder is of order n squared for the polar coding. Thus, it gives the polar coding an advantage over LDPC. Now, my friend Sami will be talking about the polar code, the performance over wireless channels.
As mentioned earlier by Maisa, a comparison in terms of complexity was done between LDPC codes and polar codes, in which polar codes have shown a better performance. Now we will go over performance evaluation of the two as a comparison between the two coding schemes. That over a wireless channel with Rayleigh fading. This comparison will be done for both image transmission and speech transmission. For image transmission, the peak signal to noise ratio PSNR was used as an evaluation parameter. Over here, the message sent was 256 by 256 pixels with 256 grayscales. As mentioned before, the channel is considered Rayleigh fading with the PBSK modulation. The PSNR equation is given over here. In image transmission, polar codes have shown better performance compared to LDPC codes, especially when the code's length is higher. For instance, the PSNR of transmitted image when using polar codes is 123.8 dB, and this is the difference between polar codes and LDPC codes, and that's for code length ranging between 2048 to 8192. Moving to speech transmission. In speech transmission, pulse code modulation was used for sampling of the analog signals. Also here, a comparison between both polar codes and LDPC was done to evaluate the performance of the coding scheme used over the wireless Rayleigh fading channel. The average spectral distortion is used. The spectral distortion SD is given in the following equation, in which over here the SJW is the original speech spectrum associated with frame J, while S prime J is the reconstructed speech spectrum associated with frame J. Now the lower the lower is the SD, with a better construction, the better the reconstruction of the speech signal is. In speech transmission, polar codes did outperform LDPC codes as well. Codes length used ranged from 2048 to 8192 bits, with code rate of 0.5. The difference in SD between polar codes and LDPC ranged between 1.8 to 2.4 decibels, with better performance of 4 polar codes over LDPC. Also a note, the higher the code length is, the better the performance of the codes, of the polar codes over the LDPC. Now to the conclusion. Being a new coding scheme, polar codes actually achieve capacity of the channel with lower complexity compared to different other used coding schemes. Also, a comparison between polar codes and LDPC was presented over a wireless channel with Rayleigh fading distribution. In this report, we found that actually polar codes did outperform LDPC for both image transmission and speech transmission, and especially for higher code length, polar codes did perform better than LDPC codes.